Until the early 1980s, queries on whether quantum effects can offer advantages in communication and computing were growing. In 1982, a paper published by Herbert showed that photon cloning can lead to superluminal communication. This would violate one of the foundations of modern physics, namely Einstein's theory of relativity. Following relativity, no information would be able to travel faster than light. This quickly triggered the two classic papers on no-cloning theorem, one by Wouters and Zurek, the other one independently by Dix. Both were published in the same year. Before going straight to the proof of the no-cloning theorem, let's first take a look at how photon cloning can lead to superluminal communication. Now, let's find out how cloning of quantum states can lead to superluminal communication. For that, we will use the diagram that we have seen previously for the superdense coding, which is the communication channel between Alice and Bob. We will label Alice qubit by qubit 1 and Bob's qubit by qubit 2 as what we did previously, but instead using the phi plus state that we used for the superdense coding, now let Alice and Bob share the phi plus Bell state. The phi plus state is the state 0, 1 plus 1, 0 divided by square root 2, and we have also seen in the previous lecture that we can rewrite these states in the plus minus basis, which is then the plus plus state minus the minus minus state divided by square root 2. So what Alice is doing on her side is now encode her information in her choice of measurement. She will have two different choices that she can measure the system. So this is her encoding. If she wants to encode information 0, she would measure her qubit, the qubit 1, in the M0 basis, which is the computational basis. If she wants to encode information 1, she would measure in the M1 basis, which is chosen to be the plus minus basis. In the first case, if she measured in the computational basis, they are sharing this state, so the qubit would be either in 0 and 1 with equal probability. So she would find out she would have a probability of having 1 equals the probability of having 0, and both of them is 50%. In the second case, again, we have this superposition, equal superposition state between plus and minus. So she would also find out that the probability of finding a state in the plus state is the same as the probability of finding a state in the minus state. That is 1/2, 50%. So now, after Alice's measurement, Bob would then conduct his measurement. So there is a time sequence between here. Bob would not do his measurement before Alice measures her state, and he will wait until Alice has measured her state. So this is all after Alice's measurement. We will then again have two scenarios depending on what the basis that Alice measured her state in. In the first case, if she measured in the computational basis, we will see that now if Alice's state is in 0, Bob's state will be in the state 1. If Alice's state is in state 1, Bob's state would then be in the state 0. So in this case, Bob will find the probability of finding his state in state 0 to be 0 and his state in state 1 to be 1. In the second case, he will find the reverse. So P0 equals to 1 and P1 equals to 0. And again, this depends on Alice's measurement, which have this half-half probability. So either case would occur with a half-half probability as well. And for the second case, Bob would not measure in a different basis. He would also measure in the computational basis. So Bob's measurement basis will not depend on what Alice's measurement basis is, because that is the information Alice wants to send. He will just blindly always measure in the computational basis. And in the first case, if Alice gets a plus, from this structure, it's easy to say that Bob would also get a plus state. And similarly, if Alice gets minus, Bob would also get a minus state. In either case, Bob measures in the computational basis, so he would have a 50-50% chance to get 0 or 1. So here, P0 equals to P1 equals to 1/2. Does not depend on whether Bob's state now is plus or minus. He will get the same probability. So now let's look at what Bob would have after one shot of measurement. He look at his measurement results. He will get either a click on the 0 or the click on the 1. And in either case, whether this is the top situation or the bottom situation, 0 and 1 occur with a half probability. In the top case, this mixture of the probability is because Alice's measurement would have the half and half, although Bob would have a deterministic measurement result for 0 and 1 state, but on Alice's side, it's already half and half probability for Bob of either getting 0 or 1. On the bottom case, Bob will get plus minus state, and for either of these states, he will get half and half probability of getting 0 and 1 on his side. So from this, he will not be able to conclude anything from just looking at one single shot measurement. So here we'll conclude that single shot measurement does not give Bob any information. So there's no information here. And there's another thing I want to emphasize here. We say that Bob does the measurement after Alice's measurement. And so the measurements are sequential, but there's no qubit that is passed from Alice's side to Bob's side, because qubit 2 is originally with Bob already with this pre-established entanglement. So there's no physical qubit transmitted. Okay? And now let's assume Bob has this quantum cloning machine that he can clone his state before doing the measurements on them. So we assume cloning. With cloning, he can make as many copies of his state as possible after Alice's measurement. So now he, other than inferring the information from a single shot measurement, he can infer it from a measurement statistics. So now let's look at how Bob can infer the information encoded by looking at his measurement statistics. In the case that Alice wants to send over information 0, Bob would only have ones or zeros on all the copies he had cloned. So he would have identical measurement result. Which is to say, all the copies would have a result 0 or 1. For example, if Bob makes 5 more copies of his qubit, they would be all 0, so 6 zeros, or all 1s, 6 1s. In the second case, if Alice wants to send over information 1, Bob would get plus all the time or minus all the time, but for either of them, he will get mixed results. Again, for the same example of measurement on 6 qubits, they will not be all zeros or all ones, but for example, he might get 0, 1, 1, 0, 0, 1. Or in the extreme case, he might get zeros all the way until the last qubit shows a measurement result on 1. But in either of these cases, as long as they are mixed, it does not matter how many 1s are there, how many zeros are there, he will have a conclusive result that the information is 1. However, in this case, even if you get all zeros or all 1s, there could be the chance that if you make an additional copy, that it might give him a different result. So this is not as conclusive as the second case, but if he has more copies that he can measure, he will get less error. Okay, great. Now, Bob has his decoding strategy, which make use of the measurement statistics to infer Alice's information. So this looks all very nice. We still need to make an argument of how this can be superluminal. So let's take a look at what is the time that takes for the communication between Alice and Bob. We will need Alice to do her measurement first, a single qubit measurement, and then Bob does his measurement. But before that, he would have to spend time copying the qubit on his side. So there is Alice's measurement, Bob's copying of his qubit, and Bob's measurement on all the copies he has. And one might even argue that, okay, there is a pre-established entanglement between them. Maybe this entanglement needs preparation time. One can ignore that because they can be prepared much in advance before Alice wants to communicate with Bob. But even if we take into the time for the preparation, it does not need to be that Alice send the qubit to Bob or Bob send the qubit to Alice. We can assume that there is a middleman, maybe Eve, who prepares this entangled state and send one qubit to Alice and the other qubit to Bob. So the time that takes for this qubit or the photon to travel is just half of the distance between Alice and Bob. Now, it does not matter how far physically Alice and Bob are separated for this protocol to work. For example, in the extreme case, we can assume that Alice and Bob can be separated by, let's say, 10 light years apart. So it takes 5 years for Eve to send the qubit, one qubit to Alice and the other qubit to Bob. And it might take some time for Alice to do her measurement, some time for Bob to copy. If he has a very powerful machine, he can do this quickly. If not, he might still take some time and then do his measurement. But altogether, the time taken could be much less than the 10 years, which is the time that would take for a photon to communicate between Alice and Bob. So we can safely claim that if Bob has the cloning machine, Alice can indeed communicate information faster than light to Bob. And that is superluminal communication. This would certainly violate Einstein's theory of relativity. Fortunately or unfortunately, this protocol does not work. Information cannot travel faster than light. This is all due to the no-cloning theorem. Next, let's see a simple proof of the no-cloning theorem.
Alright, so this is about the no-cloning theorem. We have an arbitrary given and unknown quantum state that we describe by the ket psi, and we want to copy it. So for the copy, we need an empty piece of paper, so to say. So we have psi, and this is the empty piece of paper. So this is empty paper that we write on. And now this should be converted into two versions of psi for all ket psi. So in quantum mechanics, this is done by a linear operation. And this linear operation, let me call it U, is such that U applied to psi tensor 0 gives us psi tensor psi for all psi. So suppose it works for psi 1 and psi 2. Then we ask, does it work for a superposition of psi 1 and psi 2? Psi 1 alpha plus psi 2 beta. Well, let's see. Okay, let's assume it works. Then U applied to this psi tensor 0 gives us this psi tensor this psi. So it gives us psi 1 alpha plus psi 2 beta tensor psi 1 alpha plus psi 2 beta. But because of the linearity, so this here is the cloning, the copying. But then we can also argue with the linearity. So now I'm making use of the linearity. And the linearity says that this has to be the same as U applied to psi 1 tensor 0 times alpha plus U applied to psi 2 tensor 0 times beta. And now we apply the cloning here. So this is again about the copying. And what we get is psi 1 tensor psi 1 alpha plus psi 2 tensor psi 2 beta. But then in this product, we have terms that involve psi 2 tensor psi 1 and psi 1 tensor psi 2, which are absent in this expression. So these two expressions are not the same. And therefore, this assumption is wrong. And there is the no-cloning theorem. Quantum states cannot be copied.
Now we have shown you the proof of the no-cloning theorem, which states that unknown quantum states cannot be perfectly copied. And in the case of the superluminal communication, Bob would need to copy the set of state that is 0, 1, plus, and minus. Following our proof, if we assume that 0 and 1 can be copied, then we will not be able to copy any superposition of 0 and 1. We will not be able to copy plus and minus. So there is no cloning machine for this set of state, which then tells us that there is no superluminal communication. This might seem surprising because in the classical world, we can certainly make copies of classical information or classical states all the time. If we say that classical world is a limiting case of the quantum world, why can we copy classical information or states but not quantum states? In fact, orthogonal sets of quantum states can actually be perfectly copied. I'm just writing down the statement I said. Orthogonal set of quantum states can be copied. So we look at this with the example of qubit. In the case of only a qubit system, the orthogonal set can only have two members. We label them by state 0 and state 1. They can actually be any set of orthogonal states, like plus or minus. It doesn't matter what does the 0 and 1 represent here. And the copy machine would just be able to copy the 0 states on an empty paper we denoted by 0 onto state 0, 0. And if it acts on the 1 state, and again the empty paper is in the same state, that would give 1, 1. Okay. So there are many quantum operations that can actually implement this. The C0 gate, or the C0 operation that we have seen previously, is one of such example. So if the C0 operates on 0, 0, it will give us 0, 0. If C0 operates on 1, 0, it would flip the second qubit and give 1, 1. So this type of quantum operations can make copies of the orthogonal set of quantum states 0 or 1. But it will not be able to copy any other superpositions of these states, as what we have seen in the proof of no-cloning theorem. So this is to say that this operator, for it to be a copy machine on the orthogonal set, it only acts on these two particular states. It does not act as a copy machine for the entire qubit space. And this is very similar to how classical information can be copied. As in the classical world, information are by nature all orthogonal. Classical states are also by nature all orthogonal. There is no superposition, there's no entanglement. So copying of classical information does not contradict with the no-cloning theorem. In summary, the no-cloning theorem states that unknown quantum states cannot be copied. Its proof makes use of two key features of quantum mechanics, the superposition and its linearity. The no-cloning theorem has many important implications in quantum information, other than showing that superluminal communication is not possible. One of such examples is the quantum key distribution.